First of all, I'd just like to welcome everybody here in Belfast and in Dublin to this event tonight, organised by both the IET Northern Ireland and IET Ireland in collaboration with Engineers Ireland and Cigre. We're in the third year of this event now, and turnout's just been increasing year on year, and the level of interest has been increasing every year. So a big thanks to Sony and EirGrid for hosting this event once again, third year running. There's a bit of organisation and different things within these events, so a big thanks there. Just about housekeeping, there's no alarms or fire drills planned in either location tonight, so if you do hear a fire alarm, please make your way out by the nearest fire exits there marked in the doors. I'd also ask if you have any mobile phones to check that they're on silent or turned off now as well. That'd be great. So basically the structure tonight, we have 3 speakers. Our first speaker will be in Dublin, then we'll bounce back to a speaker here in Belfast, and then we'll bounce back for the final speaker in Dublin. So I suppose all that's left for me to do is I'll run through who the speakers are, and then we'll get our first speaker up. So our first speaker will be Jonathan O'Sullivan in Dublin. He's the Innovation Manager of the EirGrid Group. John's over 18 years experience in the power industry. He's currently the Innovation Manager within the EirGrid Group, and has previously held roles as Manager of Sustainable Power Systems, Manager of Operational Policy and Performance, Manager of Market Operations, and Manager of SEM Implementation within EirGrid. And he's also held Manager of Settlement Production within ESB National Grid. He attended UCD to study electronic engineering with electrical power systems and received his PhD in 1996. In his current role, John's responsible for the facilitation of a broad innovation culture across the EirGrid Group in both Dublin and Belfast. Specific responsibilities within that then would include sort of smart grids, renewable energy system integration, including energy policy, new technologies and research. So just before we bring John up, I'll just introduce our other 2 speakers. We have Karen O'Doherty here, who's the Senior Lead Engineer for Innovation and is based here in Belfast. Karen's been working in the power industry since 2010. She holds a master's degree from Queen's University Belfast in electrical and electronic engineering, and she's also a chartered engineer with the IET. Karen is the Senior Lead Engineer within the innovation team in Sony. Her main areas of responsibility are the evolution of control center tools. This role involves developing tools to enable the realization of new operational policies, technologies, and market developments in real-time system operation. Before taking up this role, Karen has also worked in access planning and network planning, carrying out analysis of both the NI and the Irish grid. Karen is also a member of the local NIE committee, like myself. And then our final speaker will be John Lowry, back to Dublin, who is the EU SysFlex Project Director. John Lowry is his career is extended across innovation, strategy, asset management and development in the electricity sector, and he's a chartered engineer with a wide range of management experience of renewable integration in Ireland from an infrastructure and markets perspective. John helped perform key functions within the newly formed TSO EirGrid, as well as overseeing the development of new connections and implementation of EirGrid's grid development strategy. More recently, John was responsible for the commercial aspects of the newly formed system services market in Ireland, part of the DS3 programme that you'll hear more about tonight, and he's currently leading the Horizon 2020 EU SysFlex project on behalf of EirGrid to act as the project coordinator on that project. So that's our 3 speakers tonight, a lot of interesting topics there, and we'll welcome Jonathan O'Sullivan in Dublin up, Manager of Innovation at EirGrid Group.
Thank you, Brian. Thank you. I'm almost embarrassed in that CV because I didn't think I was that old, but I obviously am. I'm Manager of Innovation. Hopefully in Northern Ireland you can hear me too. I just really want to give you an overview of the broad drivers that are facing EirGrid Group, but more generally it's a global trend, and then talk about why we need to innovate, and really why we need to innovate. Then some of the innovation is the DS3 SysFlex programs that we will talk about in detail, but it's broader than that. The nature of what I think we do, I think it's good to reflect why are we doing it and what are the drivers, and that's really touch base on it, on what innovation is really. I think really if you look at it across energy systems, and energy includes heat, transport, oil, gas. I'm talking the bigger picture. There's 5 big trends. Climate change. Now, whether you believe it or not, governments around the world are beginning to act on climate change, and it's becoming a driver for action. Whether it's enough action, insufficient action, too much action, that's all a discussion as well. But it is a definite cause of why things are happening. Energy security, and I'll get into a lot of this, I think is actually a much bigger driver, particularly for Europe, and I'll talk about it, but that's another one. Fuel poverty. If we go to a world where it is solar and wind and everyone's got storage and EVs in their house, I would conjecture, and I would say more than conjecture, we're going to have an inequality issue. Whereas those who can afford those technologies can have it, those who can't. And if you then leave everyone who can't afford it to run off the system that doesn't have the ratepayer, that probably won't work. The system won't work because it won't be maintained, and the costs will have to increase on the smaller part of the proportion of the people. The rich people go off grid. I don't think that actually works, and we might have that philosophical discussion. Or you're going to have a political dislocation just when you need to make large capital investment. The politicians say we can't do this, and so that doesn't get you to a good space. But it's a challenge that we have to face. And Internet of Things is a huge game changer for certainly power systems, but energy more generally. I heard some statistics there from GE. I think there was 1 billion devices connected by 2000. So when the internet came in the late 80s, early 90s, by 2000 there was 1 billion computers connected. By 2010 there was 6 billion. By 2020 there's going to be 50 billion devices connected to this. So there's, you might know that GE are doing this thing where if there's a airline engine, it talks through the internet and sends its details as a nearly operational details. They call it twin and stuff, and everyone else is doing it. So it's not just you with a phone, which is a connected entity. It's your fridge freezer at home. It's your car engine, all of that. And suddenly you're going to have billions and billions of these things connected, and that's a game changer. And electrification. We're going to electrify, I conjecture, heat and transport to solve the bigger energy problem. We can have that philosophical discussion. No, it's not, it's something else, but we'll go on the basis. So that's a lot of the main drivers, but more generally, if we look at it, the scale of the challenge really is the big cause for energy is these people. And right now there's approximately 6.5 billion of them, and by the end of the century, there's an argument we'll go to 12 billion. So even if you double energy efficiency, which I think is highly unlikely, you're still going to need more and more energy. James Lovelock, who was one of the biggest sort of Gaia, he was the creator of Gaia theory, he's big, he actually thinks the Earth will self-regulate. That's what the Gaia theory, and you'll have about 1.5 billion people by 2100 because the Earth will get rid of the problem. But I would conjecture we'll adapt and we won't let it get there, I hope, but that's a hope rather than a belief. But that's the big issue, and from an energy total consumption, the IEA is predicting with current policies, effectively the current policies, there's going to be approximately an 80% increase in the need for energy by 2035. 60% of that comes from fossil fuels. 60% of that increase comes from fossil fuels. Now, even in the best case scenario, you're still talking about 50% increase in energy requirement. So we have a fundamental, where are we going to get this energy from? If you look at energy dependency, and you look at what the trend is, Ireland in 2000 was 95% dependent on imported fossil fuels. There was only one country with a higher dependency ratio, Israel. It really is not strategically a clever thing to do to have such dependency on things that are outside your control. And if you look at the major blocks in the next 10 to 15 years, they're all moving on oil and gas. Europe is heading from an 80% dependency on imported fossil fuel. Europe spends 400 billion euros a year on imported fossil fuels, and it's an 80% dependency rising to 95% by 2035. I argue that the main driver in the Commission for doing renewable energy and things like that is not climate change, even though that's what they sell to the masses, it's energy security, because they simply don't have it. Fully enough, the United States is seeing to that, primarily because they're going back to the oil fields in Texas and the deep wells off the coast in the Gulf Coast, and with better drilling techniques, they're getting better use out of existing oil wells. And in fairness to President Trump, he recognizes that. They have options. There was in 1971, America went, the thing that was effectively was called the Texas Railroad Commission, said go to 100%, which basically meant that America could no longer meet its energy needs itself and became a net importer, right? And they've been a net importer of energy ever since, up until it's projected, I think, in 2 years' time, where they will have enough of their own fuel online to meet their own needs. They also include fracking, things like that. But ultimately, if you go back another 50 years after that, they will go back in the same direction. So fundamentally, energy security, or we're using scarce resources, is a problem. So the solution to that is where I get to. Technology adoption is also increasing, and that's a really important. If you look at the adoption of technology more generally, the telephone took about 90 years to get 100% adoption in the States. All countries broadly follow this thing. Radio was about 50 years, microwave 30 years, VCR 20 years, cell phone 10 years. Why do I bring that in? Because from a system perspective, if we go to a place where there is very passive load to something that is now Internet of Things connected and actively being changed, that will happen at a system level very quick if the adoption at home, which I can't stop, is going to happen. It becomes a system issue. It creates a great enabling technology, but without enabling it in a coordinated fashion, it becomes a massive threat to the power system. So if you think about a line, a distribution line, it's a 38 kV line, there's 100,000 homes down at the end of the line, we say you can meet that. But we can meet it if the load, there's a diversity of the load at the end of it, that not everyone is switching in every electrical device that they have at the same time. You go to a world where they are switching in every electrical device on an Apple or Google algorithm, you have a challenge. But you have a capability, if it's done in a more coordinated fashion, to work. So the large-scale deployment of technology at scale is a fundamental challenge to power systems of the future, but it's also an opportunity. And where I also go is, I think we have fundamentally got the model of energy wrong. And it was a mistake made in 1896, which I'll come back to. But in essence, if you look at behaviours in homes more generally, somebody gets up in the morning, turns on a cooker, goes into next door, turns on a light, has an electric shower, does a couple of things. The standard watt meter that Tesla designed will tell you 2 readings. You don't know when they use the energy, and you don't know, that's over 6 months. Even a smart meter will just tell you, between this half hour I took this amount of energy. But fundamentally, when in 1896 Samuel Insull, who was the head of GE, said we're going to have, how are we going to charge for this great thing called electricity? He said, you know what we have? We have a unit price of electricity and a standing charge. You go to your bill today and you look at it, it's a unit price of electricity and a standing charge. And they've built wholesale energy markets on that law. Edison, and I still think Tesla absolutely is much better, kicks Edison's ass left, right and centre. Edison at least said at the time, what are you doing? I'm selling light and next year I have a more efficient light bulb. Meaning he wasn't selling energy, he was selling utility. And that's what the consumer actually wanted. And the model that you were coming up actually wasn't going to make him as much money as he wanted. But fundamentally, our markets need to be about the utility for the consumer rather than energy. And while we stay in the utility world, or an energy world, we're not going to be able to deliver. But the exact same thing happened in a world where we have in each home an in-home controller device that says, what I actually now know is what's being used, possibly how much energy it's taking, and I can now discriminate on utility. Noel wants a hairdryer at 5 o'clock in the afternoon, there's a certain value in that. And if we can start using this information that was never before possible and connect it to 50 billion, the fundamental possibilities on the power system are huge. The threats are very big, and the way we're going about it, dealing with it, are wrong and will lead to problems. But if we actually get into this mindset change, pivot, actually there's huge possibilities. But it's not about energy, it's about lifestyle, and it's not about the way we have done things, it's about the way that we need to do things. Which ultimately brings me to this very quickly. The money generally that we set up at the moment is in the energy and pay for it. You pay in transport, you pay for energy and heat, you pay for electricity. There might be a market in there of some sort. We put some supports around it, whether it's priority dispatch, fuel. There's a hell of a lot. There's 90 billion supports for renewable energy in 2010. There was 400 billion for fossil fuel worldwide. Carbon is around that as well, and that's actually all skewing, and then fiscal policy is all in it. So even if I come up and I say, I'm a really smart Hans and I have the better design for the electricity market, look at how many people can distort the actual investment decision to actually move it away from what it should be. And it doesn't even stop there, because if we're trying to solve the global thing, your fiscal policies, and in each section of the thing, in the EU, China, they're all doing their own thing. So if we're thinking of the system of the planet, solving that, it's going to be a bit of a challenge, a big political one. So even if I'm smart enough to think I have the right answer technically and economically, there's a political problem to getting this agreed. That's a lovely discussion. What's it got to do with power systems? Because power systems, in my view, are the solution. There's simply no better energy transfer system ever created or likely to be created, in my view. And as you electrify more and more things, the solution to the energy challenge that the globe has, whether it's energy security, climate change, fuel poverty, electrification, Internet of Things, is in the power system. But there are massive challenges in that, and simply the way we've done things is not the way we have to do them going forward. And more importantly, I conjecture that Ireland and Northern Ireland power system is at the heart and that pioneering leading edge of that system thinking to solve those challenges. And what I think we will present tonight is tangible evidence in one part of the broader innovation space that we're working in of how we're solving those problems through the DS3 problem, which is effectively a 10-year program that started in 2008 to try and deliver something for 2020. And I think we'll be able to show tangible progress. And a new project that we're looking at 2030 to really look at not only how we solve the challenges if we need more renewable energy and electricity for 2030 in Ireland and Northern Ireland, but more importantly why it's relevant for the overall European power system through the SysVec program. So that's what we want to talk to you about. Those are the challenges, which get me to the broad dynamic. We have been in a world where, to date, electricity systems have been in a command and control world. We're the TSO, you're a large generator, we'll tell you what to do, and the demand is passive. And that sort of worked when it was synchronous generation. Just combined cycle gas turbines, oil plant, nuclear plant. The tech giants are going to come in and they're going to put capability into homes whether I like it or not. And loads at home will start to be actively managed by third parties doing stuff on it that I don't really want them to do, but they're going to be able to do it. How many people have seen Smart Ireland come home, turn on your heat, turn off your heat when you want? Gotta be bored to tears. Look, you think I'm seriously going to get into that? I path of least resistance, which would make it easy for me. But it's happening whether we like it or not. So I'd rather talk about us getting on the tsunami of technology rather than waiting on the beach and waiting for it to hit. I think in Ireland the DS3 programme is about moving up here. We recognise through the DS3 programme and breaking down the barriers, and then Karen's going to talk about it, that how you operate a system. We're still dispatching all the wind farms, so we haven't quite got into this other world. that it's about lifestyle and breaking the barriers down to allow the lifestyle choices rather than just command and control. But where we want to get to by 2030 and beyond is that every demand is participating in an active way with the power system. And the system integration challenges of that, I believe, will be solved here first, which are relevant to solving it for the rest of the world, because the rest of the world are not seeing these issues yet they will see them. So that's why we need to innovate in Ireland. And broadly, our innovation strategy is split into evolving user facilitation, because we see people coming on the system, wind farms, solar, EVs, home load. Enhanced grid utilisation. It's increasingly getting more difficult to build grid, so let's use the existing grid we have better, because it will minimise it. I'm not going to talk about that, that's not on our talk, but that's part of our key innovation strategies. And reduced environmental impact. To the extent we have to build grid, let us make it the least impactful grid it can be. And that's broadly. And what we also get is, this is business model down. We start from research or a pilot down to actually implementation. That's the sort of trajectory. TSOs, in my view, shouldn't be doing research. If the answer's there, we should just go off and hire a consultant and bring it in. But there are simply challenges in Ireland and Northern Ireland today that no one in the world has solved. That's why we have to research and why you have to innovate. There's simply no one operating a power system today at 65% in real time of the overall power system coming from wind. There is simply no other power system at that level of wind and managing it resiliently. So with that in hand, I'll ask Karen in Belfast to take you through some of the bigger details of the DS3 program. Thank you.
Can you give me control of the...
Yeah, John will do it now. Speaking of control and command.
Okay, Karen, you should have control.
Yep, I think we... Okay, yeah, so we have the global context. Now to give a bit of context for here in Ireland and Northern Ireland. The background being of all the changes we're about to explain to you are we have, although we're an all-island company in the Cigre group, we do have 2 separately licensed TSOs, 2 separate regulators, a lot of different generators, some who are connected in one jurisdiction, not in the other, and different supports and different government drivers behind renewable generation in both jurisdictions. So it's not an easy task, what I'm about to explain to you, but just to understand that that's how we as a company are set up, and this is the background in which we're driving the change. So before I get into the change, why do we keep saying that Ireland is so relevant in Ireland and Northern Ireland? So this shows you Ireland as a member state of the European Commission, but we have the same targets all Ireland. So this is from the 2010 National Outreach Programme. So it shows that the targets in Ireland and Northern Ireland say we will meet 40% of our demand through renewable electricity by 2020. What it also shows you in the blue bar is that 37% of that will come from wind or non-synchronous sources. So you can see that other parts in this graph, you look at Sweden and Austria, have targets of 63 and 71% of renewable penetration. If you look at the small blue bit in the middle, they're down in single figure percentages. So on mainland Europe, they've just about maxed out the hydro storage they have there, the renewable but synchronous storage. And that's a large interconnected system. In Ireland, we're all out on our own HVDC interconnection very lightly between the island of Ireland and to GB and then on to the continent of Europe. But so we're going to see these problems first. And what are the problems? So back in 2010, I think it was, we commissioned studies to be carried out, the facilitation of renewable studies. And what those studies showed to us were that green portion of this graph here shows that 50% SNSP is a term that we bandy about quite readily. It means that we can provide 50% of our instantaneous demand can be met by renewable sources. So that can be wind, PV, or actually HVDC interconnector imports. So whenever the four studies concluded, they concluded that you could operate at 50% with minimal changes needed to be made on the power system. It said that we could move to 75%, but we would need to make some changes. And that back then, in 2010, it recommended that we shouldn't go beyond 75% in 2020. Whether that stands true today or not can be debated. But what that all shows is that if we were to continuously increase the amount of renewables, wind we connected to the system, and we weren't able to increase that system non-synchronous penetration level, curtailment of renewable resources would just continue to grow. That makes the renewable industry become less viable. They need to be able to export their generation, make money back to finance the projects. So the focus of DS3 is to keep curtailment between 5 and 7% while facilitating 75% SNSP instantaneously to allow us to meet those 40% targets on average. So sometimes it's windy, sometimes it's sunny, most of the time it's not sunny. So instantaneously we have to manage peaks well above 40% to on average across the year meet that 40% figure. And what we're saying is as a system we should be able to meet up to 75% instantaneous to average of 40% across the year. So what the facilitation of renewable studies showed is that the problems where that limitation, that 75% limitation and that 50% limitation were coming from was from system scarcities. So it looked at the inertia on the system, and if you compare 2010 with 2020 inertia, we're removing large conventional generators off the system to make room for wind and solar. And what that does is reduce the inertia on the system. And if you look at 2020, it actually showed that for about 30% of the time we would be operating at an inertia level lower than what we currently have our limit at today. So we need to find some way to address that problem. We also looked at reactive power duration curves. So specifically from a transmission system point of view, when you remove the large conventional generators, you take with them the reactive power. Most of this renewable energy is connected to the distribution system. So reactive power doesn't travel very well, which means we need more support on the transmission system. And finally, we looked at the ramping capability that's needed on the system. So if you are a weather-dependent system, your power resources are variable depending on wind, sun, whatever it is your energy source. And so what we find is that across very short spaces of time and also across longer periods of time, longer than traditional reserve products, we needed to have ramping capability built into the system to make up the slack. If there's a forecast in a wind forecast error or anything like that, we need to have that capability in the system. So what we done, as I say, back in 2010, we initiated the facilitation of renewable studies. That consisted of about 500,000 snapshots of the system and came up with this SNSP metric and the limitations. So the output of that to actually implement the changes recommended by the facilitation of renewable studies was the DS3 program. It was commented today that until they actually seen it written down, they didn't know what DS3 stood for. So it actually stands for delivering a secure, sustainable power system. So this is the logo that came along with it. It shows that DS3 isn't just the TSO making changes to itself or asking just the industry to make changes. It comes in 3 pillars. So there's the system performance. There's the aspect that we need these new generators for coming on the system to perform well. We introduced new requirements for wind. We introduced new performance monitoring metrics, and we also introduced system services, which incentivizes better performance from these generators. I'll touch on it lightly later on. System policies is the TSO looking at ourselves and saying, how can we change the way we operate the system well and securely to actually facilitate this generation? And then the bit at the bottom there is system tools, and that's us actually facilitating the delivery of those operational policies. So our control center needs to have the capability to actually operate at these edges of power system stability, and until we deliver those tools, we can't actually operate in that way. So as I said earlier, the whole purpose of DS3 is to allow the amount of wind installed to increase while keeping curtailment low. and we do that by increasing the SNSP level. So as John mentioned, we today operate at a level of 65% SNSP. So that says at any given point in time, instantaneously, 65% of the demand on this island is met up by HVDC interconnector imports, wind generation and PV generation. So as you said, you'll not hear of that anywhere else in the world. But we did have to make a lot of changes to actually get us there today. So as I mentioned, we have control of all of the grid scale wind now on the island. We enhanced the reactive and active control we have with them, and we now have very good control in both of our control centres. We don't actually carry out wind forecasting ourselves. We do procure 2 separate wind forecasts, and we merge them to try and find the optimum to actually give us good oversight. We have a tool in our control centres called WSAT, which stands for the Wind Security Assessment Tool, which is a tool that runs in almost real time, so every 5 minutes, to actually assess the stability of the system for key contingencies, be it a large increase in load, a drop in load, or growth in wind, and it actually indicates very clearly to our operators whether there is going to be a problem or not, and if they need to take remedial action to make sure that there's no problems on the system. The enforcement of standards on all generators, so we've had grid codes for the longest time. We have now just made sure that people are complying with them properly. And also through system services, when people have contracts to provide services, we've really enhanced our performance monitoring to make sure that if we incentivize performance, that we're only paying for good performance. We don't want to incentivize bad performance. And the bottom one are accurate system metrics. So we hack SNSP to whatever our level is at that point in time. So at the minute, we will not allow it to go higher than 65%. And that 65% can be made up of large-scale wind, small-scale wind, large-scale PV, and small-scale PV. So recently we updated that metric to actually take account of the small-scale stuff that's out there, but we don't actually have control of it. But we're getting some sort of aid for how it's actually impacting the system in real time. So I suppose it's not all done. There's been a lot of work, but there's still plenty more to do. One of the biggest parts of the DS3 program at the minute is rock-off, which stands for rate of change of frequency. So as we remove the large, heavy conventional generators and bring on more wind, our system gets lighter. So for the same event today, we'll have a larger change in frequency than we could have had 15 years ago when we had less wind and not as light a system. So there's 2 elements to that at the minute. There's the generator capability, so that's the large conventional generators, actually ensuring their compliance and that they won't damage themselves by actually complying with this rock-off standard. And also the DSOs have engaged in a large body of work to ensure that their loss of mains protection isn't adversely affected by the change in these settings required. I mentioned ramping earlier, so our ramping requirement is a new product that we have introduced under system services, and it basically takes account of the fact that now we have more renewables on the system. As we introduce more renewables, the error in our forecasts actually increases. So this ramping product will mainly cover that forecast error through the 3 and 8 hour time horizon. So it's not for a short-term instantaneous event, it's for the longer-term events. I mentioned system voltage control there too. We have a large reduction in the amount of reactive power we have on the transmission system, so we are maximising the support we can get from the distribution system and actually working with both the DSOs to allow the transmission system to benefit from a lot of the reactive capability that's actually embedded there. And maintaining transient system stability. So that glue that holds the system together, be it the large generators, is disappearing, so we have to work to ensure that we're not putting the system at risk for an event. So a lot of those things can be covered through new policies or new requirements on generators, but some of it just won't. Some of it we have to incentivise performance. So that's through the DS3 System Services Programme. We have incentivised performance. We've moved from 7 services in the past to 14 services over a wide range from milliseconds right into hours, and it's not just frequency, it's reactive support too. But what we're showing here is, John mentioned it earlier, that it's not just energy anymore, it's all about the services. So traditionally, the variable cost of your generator would be made up of energy payments, would be that fuel cost. Then the capital cost would be made up of capacity and a bit more of that energy, and the ancillary services payment was tiny on top. It was just the cream on top. Whereas going forward, with more resources connected to the system, the variable cost of generation actually goes down, and the capital cost is the larger proportion of the cost that it actually takes to build that generator and run that generator. And then system services will be worth much more in the future than it is now. We're going from a place where we used to spend around 50 million a year on system services to 235 million annually by 2020. So there's a lot of movement towards a services-driven market. Oh, frozen. There we go. So with all these things, we've actually facilitated us now operating at a 65% SNSP limit. So it shows that we get green line there, because whenever we trial, John mentioned that we always trial these things before we make them operational policy, and we usually trial for at least 100 hours. So we run the system in a mode where we see how it behaves between 60 and 65%. We then carry some offline analysis to ensure that if there was a system event happened during that time, that the system would have been okay. And actually this week it became an enduring system policy. So now, as a matter of course, it's business as usual. We will allow the system to operate up at 65%. And we do. So this is across a 2-day period. So it's just highlighting that there are periods of time, up to long periods of time, or days, day and a half, where we're operating the system at high levels of SNSP. It's not just for an hour here or there. When it happens, it can happen for a prolonged period of time. But you can also see that it can ramp up and ramp down quite quickly. So that's where we have to have the flexibility in the system to take account of that variability. So all that might be well and good if we've never actually been tested either. If there was never a storm and we never got tested, then we could never prove that it's all working. But we have a couple of examples. So back in 2014, Storm Darwin, there were wind gusts in excess of, I think it was 160 kilometres an hour measured during this storm. There were poles down left, right and centre. You can see there are 110 wind pole. It had rained for about 3 or 4 days before the storm, so the ground was really wet, so everything was weak already. What you can see on the right-hand side there is the wind forecast. So we lost over a gigawatt of wind in a very short space of time. And what actually happened was, as the storm travelled across the island, we had a period where there was low wind in the north of the island, and high wind in the south of the island. So in the eye of the storm up north, while the storm was still down south. So there was a real mismatch of where the generation was, and it wasn't the same scenario for the entire island. But there were stations lost, wind farms were lost, but the system never went down. So in our book, that's a success, and we still operated at high SNSP. And more recently, we had Hurricane Ophelia. So we had good warning that this storm was coming, and we actually preempted the wind curtailment. And you'll see here that the demand curve was actually more like a Christmas day. It wasn't like the normal day we would have expected, because people didn't go into work, people stayed at home. But they managed wind in real time that day to actually closely match the demand curve profile. And they split the island up into different regions and matched the demand and generation in that region to ensure that if we lost a large portion of the island, the other parts of the island could actually stay alive. So on that scenario, wind actually helped us maintain system stability. So before I hand over to John, I just want to talk a bit about how all of this is relevant to Europe. So what this shows is by 2050, Europe wants to have 39% of their energy mix to come from electricity. So if you look at, that could be anywhere in the range of 42 to 55%. So if you take 39% of 97%, you actually get 37%. So what we're doing now by 2020 is what Europe wants to do by 2050. So what we're doing here today, they're going to see in 30 years' time. So it's actually really relevant that the services, the market constructs, the tools, the policies, and the performance that we have here today will all be relevant to Europe in 30 years' time. And just to prove it, there was a bit of analysis done, the same analysis was done for Ireland and Northern Ireland, we done in Europe. And we actually found that Europe sees the same scarcities as we do. They will in the future. The same three, so for inertia, reactive power, and for ramping. So we just have to wait until 2050 to see if they see the same problems. But John is going to explain to you how Sysflex is doing that.
Okay, Karen, we have control now. Good evening, ladies and gentlemen. So, before I get into this presentation, I might just highlight, well, why are we getting involved in this European project? And I think testament to that is that what Karen was talking about earlier is the fact that we are now in a position to operate safely and securely our power system with levels of 65% renewables. That is, it is world beating, and we believe that Europe has a lot to learn from what we're doing here in Ireland, and we believe that European policy needs to move in the same direction of this system thinking. So what I want to do first of all is maybe just talk a little bit about the Horizon 2020 scheme or the fund, because it is it's a wonderful opportunity for entrepreneurs and enterprise to get funding for projects that they're looking to get up and running. And I'm not sure how much people really understand the availability of this fund or the calls that are out there, but it is something that I think, if you are involved in business development at all, that this is something that you should look towards for research and innovation projects in this space. It's an overall it's a financial instrument basically of funding from the EU, and it's aimed at securing our competitiveness across three pillars. Its aim is to develop excellence in science, industrial leadership, and address societal challenges. And we, together with our partners, put together this proposal last year under this Secure, Clean and Efficiency programme, and secured 26 million of a grant last year. There were 3 other projects that were successful in this call, but it's just an interesting one, and I think everybody should be aware of what's out there. So what was this call? Well, it was a demonstration of system integration with smart transmission grid and storage technologies with increasing share of renewables. So basically it's renewable integration on a pan-European basis, up to 50% by 2030. So we came together with 34 other partners across Europe, across the industry, across the sector, which I'll go into a little bit more detail, to come up with a solid proposal or a project that would examine this area. So maybe I'll just talk a little bit about the challenge. What is it that we're trying to address? Well, today, on a pan-European basis, so renewables are meeting 30% of our needs at the moment. But the desire and the policy target is to get to 50% by 2030 and beyond. So I don't know if you can see this this graph very well, but essentially the mix of renewables that we have at the minute on the system across Europe is largely met by hydro and pump storage. Obviously here in Ireland we have a very, very large percentage of wind on our system, but across Europe it's actually hydro makes up the majority of it. And that is something which has been very stable for a long time. So you'll see on this graph here, this is the hydro element. And we don't expect that that's going to change. We maxed out on hydro. So we need to source our renewable energy from other technologies across Europe over the next 10 years if we're going to meet that target. And I believe that most of that will come from wind and solar. Other dimensions, as John alluded to earlier, is the electrification of transport and heat. So as well as population increases, we also have a shift towards electrification, which is all leading to pressures on the system from a demand perspective, but also from a system operability perspective in terms of the complexity of the system. Another dimension then is obviously storage and large-scale battery storage, which is both an opportunity and a challenge, because battery storage, like EVs, like I suppose the smarter living space, is all creating greater complexity from operating a transmission system. In addition, the structure of grid and where energy is sourced. So John alluded to centralised command and control, where we have very, very large generation facilities across Europe. And that is shifting to a much more decentralised and distributed grid or distributed source of energy down to micro generation, down to residential generation, solar for example, and battery storage. So all of this is adding to the complexity of how we operate the transmission system. And based on our experience, we recognise that the key to this is flexibility and having a very, very flexible grid to allow you integrate large volumes of renewables onto your system. Hence the EU SysFlex, it's in the name, it's a flexible system for Europe. So what is this project about? So key to this will be developing operational solutions for system operators in this future flexible environment. The identification of market and regulatory enhancements to incentivise the market to facilitate flexibility. Technical solutions to deliver on it also. So it's the capability of plant and technology to deliver more flexible solutions. And ultimately what we're talking about here is designing a roadmap for Europe based on the work that we will do from a scalability perspective and a replicability perspective, and ultimately influencing EU policy direction. So the consortium is a very large consortium. We think it's a very strong consortium represented right across Europe. We have a number of TSOs, DSOs, technology providers, generators, research and academic institutes, and so on, and some consultancy involved. So it's a very, geographically, it's very well spread. From a sectoral perspective, it's very, very well represented. And we think that each aspect of this partnership will lend to positive outcome. And we also have a very strong advisory made up of TSOs and representative bodies. So just to give you a little bit more detail about the project itself and what we're going to do, Noel Kniff, who's here this evening, is leading a very, very important element of this project, which is really about identifying the system need, the system scarcities on a pan-European basis. So together with the Ireland, Northern Ireland experience and studies that will be carried out, EDF are looking at it from a pan-European or a mainland European perspective. As I mentioned earlier, we're looking at market and regulatory enhancements to facilitate the system change that is needed. Identification of flexibility capability through the demonstration projects that we're running, as well as the qualification trials that we're doing here in Ireland. Developing support tools, and policies and procedures to facilitate this, and I said ultimately developing a roadmap for Europe. So where do we fit in on this project? We're the overall coordinator. We're leading the consortium. And all these blue elements here is where we're involved. As I said, Noel is leading this piece of developing new approaches to operating in this high-res environment. We're also involved in this work package that really essentially, from an EirGrid and Sony perspective, is looking at a qualification trial process, and Karen, who's up in Northern Ireland, is leading that work package, which is potentially is a very, very interesting route to market also for new technologies and capability of plant. Data management and data exchange is obviously something which is very, very important. We're involved in that. And I suppose ultimately what we're talking about here is the exploitation and dissemination of information about the project and its outputs. I mentioned earlier that there's a number of demonstration projects across Europe. So we have essentially seven industrial scale demonstration projects. So this is actual demonstration of system flexibility or capability on the transmission system and distribution system. So there's a number of projects that are looking at low voltage or medium voltage capability and the services that can be provided to the transmission system. There's a data management and a data exchange platform project being run by Enering in Estonia, which is a cross-border project between Estonia, Poland and Latvia. Another one in Italy Germany, Finland, as I said. EDP in Portugal are looking at the capability between wind and hydro plant and the services that can be provided to the transmission system. EDF, I was going to show you this little video. I think it's an interesting little video of their concept grid. So they actually have a concept grid, a physical grid that's built in Paris, that we're going to use to test and try flexible capability. And I'll just show you the video because I think it's a really interesting one. I'll probably finish on that if it works. Have we got volume on this cylinder? Are we down, dude?
Located in southern Paris on the Renardière site, EDF's R&D division has created Concept Grid, a major experimental platform designed to anticipate and support the development of electrical systems. New challenges must be overcome to integrate fast-growing photovoltaic and wind turbine generation, as well as new uses such as electric vehicles and heat pumps. In this context, EDF is committed to these developments and conducts various experiments, both in laboratories and under real conditions on the grid. Tailor-made to suit these needs, Concept Grid is at the crossroads between these two approaches to safety conduct. Complex testing campaigns that would be impossible to perform on a real grid. Concept Grid extends over 3 hectares of Le Renardière site. Its very core is composed of numerous means designed specifically for this project. A control center to operate the network and monitor the tests, a primary substation which distributes the electrical current, over 20,000 volt overhead and underground medium voltage grids, a low voltage grid with 7 kilometers of underground cables and an overhead line, a reduced scale residential area enabling the connection of novelty equipment of tomorrow's consumers, a platform dedicated to detailed tests on electric equipments, allowing, for example, comprehensive studies on storage systems. The protection and control system of the grid uses telecommunication networks. These networks are also used to monitor the experiments. In order to better represent real distribution grids, the Concept Grid residential area integrates the following capabilities: photovoltaic and wind turbine generation, consumption including heat pumps, and storage. For further studies, Concept Grid is also electrically connected to other EDF testing laboratories and facilities available on the site. This unique platform is used to test equipment and systems under normal or disturbed operating conditions, representing those encountered on the existing distribution grids. To achieve this, electrical equipment installed in the main building are used to reproduce the behavior of larger distribution grids. All of these elements composing the Concept Grid can be adjusted as desired to offer a very large choice of study and experiment. Electricity consumption can thus be optimized within a residential area, and remote readings can be taken or anomalies remotely detected thanks to the use of smart meters. Equipment as well as service offers can therefore be tested. With interchangeable equipment and the possibility of hosting new infrastructures, Concept Grid is a progressive tool that adapts to suit the emerging needs of smart electrical systems. In this field, Concept Grid is positioned as a reference laboratory in France and abroad. Open to long-term partnership as well as one-time collaborative work, this is the privileged gathering platform for all the stakeholders: equipment manufacturers, network operators, electricity suppliers, laboratories and universities, all stakeholders which, thanks to Concept Grid, can now prepare the electrical systems of tomorrow.
So that's just give you an idea of some of the, I suppose, the opportunity we have to engage with our European partners, although I think John might he'd like to test their smart meter capability, or lack of smartness maybe, you might argue. So that's it really. Just wanted to give you an overview of